Okay, thanks for organizer for giving me presentation today. I will talk about how we prove the optical response of Chiral Phonons in lead telluride using the continuous wave terahertz radiations. And first we start with the motivation, and some of this part overlap the Professor Biden's talks yesterday morning. And next, I'll talk about the experimental setup and method. This is more technical experiment. Then next, I will show you the result of our Faraday effect. And I will also share the future plans. Let's consider the dynamical multiferricity. The time-dependent dynamic electric polarization induced the magnetizations and some circular motion of ions induced the local magnetic moment. And the ions have different mass, then the effective magnetization is generated. And in this paper, the orbital magnetic moment of phonons is calculated for various materials, and we focused on lead telluride. And the lead telluride has a symmetric crystal structure, and this phonon mode is linearly polarized with opposite directions. And this monomode also shows the circular motion of ions and carries the orbital angular momentum, and also split into left and right circular polarized phonon, and then it called phonon-Siemens splitting. But when the magnetic field is applied, the ions move the circular motions, and the phonons transform into the circular polarized vibrations. And then sorry, I confused. Yeah, without and with magnetic field, I'll skip this one. And I would like to introduce this paper, and this paper also Professor Biden's talk in details. So I will briefly give an overviews. And these groups use the terahertz time domain spectroscopy to study the transverse optical phonon mode. And this transverse optical phonon mode shows us phonon softening. And this phonon shows in the terahertz. So we picked these materials. And this phonon also shows on harmonicity. And with the magnetic field, lead telluride shows the magnetic circular dichroism, which is different absorption between the left and right handed circular polarized light. And at low temperature, the magnetic circular dichroism is around 30%. And they also confirm the phonon-Siemens splitting in lead telluride, and they extract the G factor using this equation, and this G factor is very larger than the after calculation with the harmonic phonons. And now, following the previous studies, we take a different approach to study the phonon mode. We use the frequency domain terahertz spectroscopy And the backward wave oscillator is used as the source. And this backward wave oscillator generates the continuous wave. And even though this source generates the continuous wave, it is also can tuned over the range of plus minus 30% at central frequency. And this frequency covers from 1 to 40 wave numbers. And this range is very important for us to study the chiral phonon in lead telluride because the optical phonon mode exists in this range. And the terahertz radiation passed through the wire grid polarizer, and the first wire grid polarizer oriented at 0 degree, and we used it to ensure the incidental light makes the linearly polarized along the y direction. And after passing through the sample, it goes through the second wire grid polarizer at minus 45 degree or 45 degree. It is used as an analyzer to detect the polarization of the light. And this terahertz radiation is detected by the color cell. And this photo is our real experimental setup. And this is the backward wave oscillator as a source, and we performed the transmission measurement. And this is the detector color cells, and our sample was mounted in the magneto-optic cryostat, and this magneto-optic cryostat can control the temperature to Kelvin to 300 Kelvin and the magnetic field up to 7 Tesla. And the magnetic field also could switch the direction. And our sample is the lead telluride thin films, and this lead telluride thin film with the 50 nanometer thickness and grown on indium phosphide. And my experiment is deeply related to the Faraday rotation, so I will briefly explain the Faraday rotation. As may you know, when the linearly polarized electromagnetic wave pass through the materials, then the polarization plane rotates, and this angle of rotation is the Faraday angle, and it allows due to the circular birefringence. If the material has the different reflective index for left and right and the circular polarized light, then the incidental lights experience the relative phase delay. And in general, measuring the transmission at two different arbitrary angles is enough to calculate the Faraday angle. And we chose the plus 45 degree and minus 45 degree because we can explain by the Mallet's law. This equation indicates that how much intensity changes depending on angle between the light polarization and the polarizer axis. And the red is the zero Faraday angles, and the blue is shifted by the Faraday angles. And in the red curve, you can show the derivative of a cosine squared graph is greatest at the 45 degree and minus 45 degree. So That means small Faraday angles produce a large measurable difference in the intensity. So that's why we choose the 45 degrees. And then we can calculate the Faraday angle using the minus 45 degree and 45 degrees transmitted intensity. And now this is our experimental data. And one of the advantages of a backward wave oscillator is we can measure it at fixed frequency and sweep the magnetic field. That means first data, we fix the frequency 0.3 terahertz and sweep the magnetic field from 6 to -6 or -6 to 6. Then we measure the two different transmission intensity depending on analyzer angle. And this difference between the analyzer angle is directly related to the Faraday rotations. So as a magnetic field increases, the Faraday angle is also increases. And we also measure the bare indium phosphide substrate to distinguish the substrate contributions. And this measurement was performed the identical condition, and all our measurement was conducted at the same temperature, 10 Kelvin. And this is our result of the Faraday rotation. And as you can see, the Faraday rotation increases as the magnetic field increases and the saturate above the 3 Tesla. And if the this magnetization comes from some spin, then we would expect that some hysteresis loop was shown, but in our data, there is no hysteresis. So we expect that comes from some magnetic induced and likely originally from chiral phonon induced magnetization and not from the spin. And one thing is that at high magnetic field, we can see the Faraday rotation is nearly 300. The lead telluride is a non-magnetic material, but this value is significantly large. So we expect this behavior is related to the chiral phonons. And we also check the indium phosphide substrate. And unfortunately, this indium phosphide substrate also shows the Faraday rotations, but relatively small. And when we subtracting the indium phosphide from the lead telluride thin film, this strong Faraday rotation also remain, and the reversible behavior depending on magnetic field is also observed. So we think this behavior comes from lead telluride. And we measure the other frequency, the 0.316 terahertz. And this data is consistent with the previous data. And the data looks more noise due to the low transmissions. But after the indium phosphide substrate subtracting from the lead telluride sample, we can also see the same behavior, the no hysteresis and saturation above the 3 Tesla. But now we don't know that really comes from the chiral phonons. So this is our next steps of our experiment. First, we should change the indium phosphide substrate because our indium phosphide substrate has a low transmissions and transparent to only below the 20 Kelvin. So we want to change the terahertz transparent substrate, for example, the barium phosphide, barium fluoride. And then after that, we can measure the phonon absorption difference using the circular polarized terahertz radiation. And this circular polarized terahertz radiation can generate by the two methods. One is very easier method is using the quarter wave plate. But I will introduce the second method using the polarization converter. This is a polarization converter, and this converter consists with the movable mirrors and wire grid polarizer. Then when the light incident and the X components of the light transmitted the wire grid polarizer and reflected by the moving mirrors. But the Y component light reflected by the wire grid polarizer. So after that, the phase difference between two components can adjusted by the distance of between moving mirror and wire grid polarizer, and the phase difference becomes a pi over 2 or minus pi over 2. We can get circular polarized light. And left-handed circular polarized light and right-handed circular polarized light is depending on the sign of the phase difference. And we also confirm the circular polarized light using that setup. And this is a graph intensity depending on analyzer angle with polarization converter and without the polarization converter. When you can see with the polarization converter, this line is more flat, and when the degree of circular polarization is close to 1, we can say that there is a perfectly circular polarized light. Then this line is 0.97. And I would like to thank for our institute member, Professor Martin Drosa and Dr. Atem and Luca. And this is our collaborate with provide the sample, Professor Eric and PM from Eindhoven University of Technology, and this research was supported by the National Research Foundation of Korea. In this is summary, we measured the Faraday rotation in lead telluride using the continuous wave radiation, and we observed the strong Faraday rotation. And we would like to suggest that this comes from the chiral phonon or contribute some magnetic optical response in lead telluride. Yeah, thanks for attention.